Today we want to look at the second part of the fundamental theorem of calculus. The setup is that we need a continuous function on a closed interval, and for the second part, we're going to need some value from that closed interval. So that's what that opening line is. That's the requirements. Part one is of the fundamental theorem of calculus is the part that we're familiar with. The definite integral from a to b of f of x to x is capital F at b minus capital F at a, where capital F is an antiderivative of little f. This is saying that the definite integral of the rate of change of a function on an interval is the change in the function on that interval. That's our way of interpreting what's going on. Thinking about the relationship between a function, capital F, and its derivative, little f. The bigger picture of what we're doing in the first part of the fundamental theorem of calculus is that we are using an antiderivative to calculate a definite integral. We want to calculate a definite integral, we use the antiderivative to do so. And in this case, we're thinking of the definite integral as an area, or more philosophically, we're thinking of the definite integral as a continuous sum. The second part of the fundamental theorem of calculus is just the reverse of this. Here's how we write it. We say capital F of x, defined to be the definite integral from c to x of f of t dt, is an antiderivative of little f. In this second part of the fundamental theorem of calculus, we are using the definite integral to construct an antiderivative. We are using the definite integral to construct an antiderivative. We are using a definite integral to construct an antiderivative. Not find an antiderivative with a, let's say, x to the n plus 1 over n plus 1, but to construct an antiderivative. The reason that this matters is that constructing an antiderivative, finding an antiderivative is not always a nice process. All we have right now is x to the n plus 1 over n plus 1. So we're like, oh yeah, finding antiderivatives is easy for now. It's easy for now. So the reason that this is important is that we're using the definite integral to construct this antiderivative. The reason that this matters is that definite integrals can be approximated to any degree of accuracy by finding area, length times width. That's what's useful about this part of the fundamental theorem of calculus. That's the important thing. So the important thing, the reason that we care about this is that definite integrals are area, and we can approximate definite integrals to any degree of accuracy using area. We can approximate definite integrals with area. The reason that this is important is that there are some functions that are not derivatives of anything nice. Some functions do not have nice antiderivatives. Some functions do not have nice antiderivatives. I'm putting nice in quotes because it's a shorter description of what I want to get across. Sometimes we say this by saying some functions aren't the derivative of anything. Anything nice. When I say nice, I mean a finite combination of elementary functions. And now you can see why I said nice. So when we say nice, we mean that some functions do not have antiderivatives that are finite combinations of elementary functions. Some functions do not have antiderivatives that are finite combinations of elementary functions. There's two things that are going on there, the finite combinations and the elementary functions. That means to describe these antiderivatives, we need to use non-elementary functions by constructing them, or we need an infinite combination of elementary functions. So since there are two requirements, there are two ways we can get around those requirements, two ways we can break those requirements. So the opposite of finite combination of elementary functions is two things. Non-elementary functions, finite combinations of non-elementary functions, or infinite combinations of elementary functions. Not A and B is equal to not A or not B. Everybody remember that from your formal logic course? No one takes a formal logic course. But it's really just like the important thing to remember is that when you're talking to a mathematician, when you say or, you're including and. So don't say and or. Just say or, because I'm going to assume and is included in that. As far as elementary functions goes, elementary functions are all the functions that you're familiar with. Those are just like your polynomials, your rationals, radicals, exponential, logarithmic, trigonometric, inverse trigonometric functions. Those are all elementary functions. We didn't call them that because we didn't need to until now. So elementary functions are just the ones that you're familiar with. Non-elementary functions are the things that we have to construct for now. So the second part of the fundamental theorem of calculus says that if we have a continuous function on a closed interval, we can make an antiderivative. Even if we can't find an antiderivative, we can build one. So that's the important thing. Even if we can't find an antiderivative, I don't know why I have to say it this way. If we can't find an antiderivative, we'll just build one. So, for example, some extremely important functions do not have antiderivatives. So, for example, e to the negative x squared is not the derivative of anything. E to the negative x squared does not have a nice antiderivative. We can't write a function where we take the derivative and come up with e to the negative x squared. We have to build one. Oops. We can't just write a nice function down. We have to construct one using the second fundamental theorem of calculus. This is not as nice as being able to say something like an antiderivative of x squared is 1/3 x cubed. Makes a nice, clean, closed formula. Here we're constructing one. It's not as satisfying, but it's perfectly functional, because if I need to know what f of 1 is equal to, I can approximate this to whatever degree of accuracy I have available to me. So I can just math 9 this and say e to the negative x squared with respect to x from 0 to 1. So f of 1 is 0.747. I can evaluate this at 2. And I can evaluate this at 3. I can evaluate this wherever I need to evaluate it. I can come up with an approximation to any degree of accuracy depending upon my computing power. I only have so much computing power right now because I've got this massive TI-84 computing power, which is from the 90s. And it really hasn't changed all that much, including the price. I don't know how this works. It's just like, it's amazing. Imagine the computer that you had. Oh, wait, none of you had a computer in 1995. Because none of you were alive and you were like negative 10 years old. Imagine your first computer. I don't know if you know how much it cost. Would you buy that same computer for the same amount of money today? It's like, oh, hell no. But like when these TI-84s came out in like the 90s, they were like $110, $130. If you want to buy a TI-84 now, same technology. I mean, it's got like I don't have to use batteries on this one. It's rechargeable, but same price. And it's also sold as a graphing calculator, and it's really not very good at graphing. Anyway, feels like a trick. So this is the second part of the fundamental theorem of calculus. We can use a definite integral to construct an antiderivative. Right now, we're only at the beginning of our antiderivative journey. Sometimes we will not be able to find an antiderivative, but we can always build one if we can't find one. Any questions? It's important to also to remember that when mathematicians say we don't have, this is not the derivative, it doesn't mean that we haven't found it yet. We have shown that there isn't one. So it's important to know that distinction. When we say something like 1 divided by 0 is undefined, it's because there can't be a value. Not that we just haven't gotten around to figuring out what value it should be. There can't be one. When we say pi is irrational, that means it's not the ratio of integers. We have shown that to be true. We're not just like, oh, well, we just haven't figured it out yet. Does that make sense? It's important to understand what mathematicians, when mathematicians use words, they mean certain things. How's everybody okay? Everybody looks so stoked. Actually, I took my glasses off. So in my mind, I could just hallucinate big bright smiles and everything. Yay. That might be the hallucinogenic properties of the coffee I made. I'm just kidding. I didn't make hallucinogenic coffee this morning. I made it last night. It has some fermented. Just kidding. I'm not hallucinating right now. But now, no. Yesterday, I had promised that you would have some problems similar to the problem that we worked on yesterday. And I did not change, hopefully I changed the names all the way through. I think I changed the names from G to P all the way through, and I think I got the capitals in the right places. So same thing. All I did was flip this around. Apparently I flipped this around the x-axis and the vertical line x equals 3. So it's just a slight variation, but I want you to read the intervals of increase, the intervals of concavity. Remember that the graph that you're looking at is the derivative of the function we're interested in. The function in which we are interested in. You can use your notes on this. I encourage you to do so. You can use your classmates on this. So help each other. This is a paper that you will be turning in. And it'll appear online, probably except for the graphing parts.